Don't stop the music tonight. Okay, what do we got here? We're looking at a Unit 3 E2 problem. These are the simultaneous motion problems. And this is the second one we're looking at. It's the one with the rowboat and the motorboat. So we have a rowboat here, row your rowboat, with a small leak. Ugh. So the rower puts up a distress flag and begins rowing towards the shore at a constant speed of 5.2 meters per second. Now that constant speed immediately lets us know what the acceleration is. It's a 0 because they're not speeding up, they're not slowing down. And what happens here is a motorboat traveling by at 16.7 meters per second, same direction, notices the flag just as it passes the rowboat. It immediately begins to slow down at a rate of 2.6 meters per second. How long does it take for the rowboat to move beside the motorboat, and then how far did the rowboat move? So let's do this. Here is the water, and here's our little green rowboat. Whoop, I'm a rowboat. And then here is our sweet motorboat. I don't know how to draw a motorboat, but it's fast. You can tell because of the way it is. So what's going to happen here is our rowboat, as it's moving up here, we know it has an acceleration of 0 meters per second squared because it's at a constant speed. And we know it has a velocity here of 5.2 meters per second. Now technically this is the initial and the final velocity, but it won't matter when we go ahead and use equation 5. We'll just call this the initial because it's going to hold that. Okay. Now, once this motorboat is here, the motorboat is booking it. It's got an initial velocity of 16.7 meters per second. And what's going to happen is as this motorboat moves past the rowboat, it's moving so much faster that the motorboat's actually going to zip down here as the rowboat's like, oh, I got to get to the shore. I got to make sure I don't drown in the boat. And then the motorboat's, it's going to slow down going out here. It's going to stop for a second. And then it's actually going to start moving in the opposite direction. And at some point, as this rowboat is still rowing, they're going to reach the exact same point. And when they reach this exact same point right here, that is the end of this problem. Okay? So we know if the rowboat is going to be slowing on the way out and then speeding up, going back to the boat, we know that this acceleration needs to be acting to the left. We're calling velocities positive that are going to the right, but that means values going to the left are negative, which means that this acceleration here is going to be a negative 2.6 meters per second squared for the motorboat. Okay, because it has to slow down, so the acceleration and velocity are opposite directions, and then it has to speed up to get back to that rowboat. Okay, so now that we're looking at this, we have acceleration and velocities for both objects. And since we have two objects in this type of problem, we are going to use equation number 5 from our best friend. And we're actually going to use it for both the rowboat and the motorboat. Okay? If you don't have a best friend, equation number 5 is the one that looks like this for motion equations. It is a delta x equals the initial velocity multiplied by time plus a 1/2 at squared. And if you don't know where that's from, you should check out Teach You Again. Okay? But that's the equation we're going to use. And we're going to use it for both objects. So if I write this equation number 5 out for the rowboat, well, I don't know what delta x is, and that's fine. It's just some value. Okay? It's just a delta x. Because that delta x is actually going to be how far the rowboat traveled. And that's technically the same displacement as the motorboat. Yes, I know the motorboat went out further and then it came back, but that's a distance, remember? And with vectors, we're talking about displacements. We're talking about starts and finishes. So for the rowboat, we have a delta x, the displacement equals, well, the initial velocity is 5.2, and then multiplied by a time. Okay. Plus 1/2 at squared, but since the acceleration is 0, all of this is going to be multiplied by 0, and it goes away. So we can just end the rowboat's equation like that. For the motorboat, we're going to have the same delta x because it starts and stops at the same position, right out here. But we're going to have a longer equation. We're going to have an initial velocity of 16.7 times t, and then plus, because it's accelerating, the 1/2 times the acceleration. Really, classroom? You got to beep whenever I'm doing stuff. But it's 1/2 times the acceleration, which is negative, so negative 2.6 meters per second squared, multiplied by time squared. okay? And so that's equation number 5 for both objects. That's equation number 5 twice. And if you get to this part, you successfully have accomplished all the physics. You're a hero. You're a champion. Way to go. Way to be. At this point, it's just a math problem. Because both of these displacements, the delta x, are the exact same, and we know one of these terms for delta x, we can actually use a substitution method and replace a delta x with t's. We actually need to do this because if you notice here, there is one unknown and two unknown in the single equation, and that's not possible to solve mathematically. We would need a second equation, which we have here in pink, in which we can combine these together. For two unknowns, we need two equations to solve them out. So let's do that. If I put the 5.2t down below for delta x, we're going to have 5.2 times t equals, and then everything in pink. So 16.7t plus 1/2 times negative 2.6 multiplied by t squared. Okay? So that's what we have now. We just did that substitution to get the 5.2t down here. At this point in time, we just need to solve this for t. I'm going to subtract 16.7t from each side. And I can do that because these t's with the coefficients, these are like terms. So on the left side here, I'm going to get negative 11.5t equals, these have gone away. And then on the right side here, to rewrite this, 1/2 of negative 2.6 is negative 1.3. And that's going to be t squared. Now, a kind of cool thing here that math departments don't exactly like, but in physics, we're going to do it anyways, is we're going to actually divide each side by t. Math departments will say, oh, but t could be 0, and that means you're dividing by 0, and there's an issue there. But we know that we don't care about t equals 0 because t equals 0 at the beginning of this, and we know they're side by side there. What we want is some time later. So we know we're not dividing by 0, so who cares? And by doing this, by dividing by t on both sides, I get rid of that t squared with the t down below. So all I have now is negative 11.5 equals negative 1.3 multiplied by t, and now we can divide by the negative 1.3, whooshing, divide by the negative 1.3. We see our negatives here divide out, which is nice. And we end up finding that the time here is just 8.8 seconds. Okay, so that's our answer to part A. To find the answer to part B, we simply take this time and that was weird. We take that time of 8.8 seconds and we just throw it back up into the original equation. We know what the time's going to be. This allows us to solve for delta x, or how far the rowboat went. If we wanted to, we could have actually put the time into the pink equation here to solve for delta x, but that means I've got to square it and then multiply and then add it to something else. That's just a lot of work. I don't want to do it. So it's much easier to put it into the simpler equation if you have it, and you can solve for delta x there. Okay? So with that, that's a simultaneous motion problem. It is, from a physics perspective, it's not that crazy. You're drawing a picture, you are using equation number 5 twice, and then the physics is over. From a math perspective, you got to keep going. You got to keep grinding out the algebra. You got to keep going and going and going until you get that final answer. Okay? Make sure your final answer isn't negative. You cannot go back in time. That's be kind, rewind kind of stuff, and you can't do it. So you're not allowed to go back in time. You can't have a negative there. And just be careful as you're substituting in. I tend to see students, they're trying to add t and t squared terms together, and you can't do that either. So just be careful with your algebra as you're running through this. But in the end, you'll be just fine on this one. Okay? So that's how you set up a Unit 3 E2 simultaneous motion problem. But for now, we are finished. Adios, and y'all take it easy.